Hey everybody, welcome back to yet another Codeforces channel. Today we will talk about minimum spanning tree, an essential topic in graph theory. So first I'll explain the problem itself. What is a minimum spanning tree and what properties does it have, etc. Then we'll talk about two main algorithms that you absolutely have to know. And lastly, we'll cover a couple of exercises, 4 to be exact, from the gym. So the link to the gym will be in the description as usual, and the same goes for my solutions. They will be published on GitHub, and I'll add a link into the description. Okay, so let me pause the demonstration and let's get started. Okay. And I'll grab myself an empty space here, a bit of empty space. And let's look at some graphs. So as promised, we have a weighted graph. So the edges have weights. Let me draw something like that. Potentially, yeah, that's better. Suppose we have somewhat complicated graph. Let me also add some realistic numbers in. So potentially we may have a graph that looks like this. It has 4 vertices and a couple of edges, 5 edges. All edge lengths are distinct, and we want to find minimum spanning tree. So the minimum spanning tree, which is commonly abbreviated as MST, is a connected subgraph of our graph, right? So first it has to be connected. Yeah, connected. And second, it has a minimum total edge length. Okay, so each edge that we take into the graph, it has some weight. Let's say we abbreviate by WE, the weight of edge E. And we take the sum of all edges that we took into our MST, and we want to minimize it. So in the example above, let's see what would be an MST. I think that MST in this case goes as follows. We take this edge, and take this edge, and we take this edge. Right? So the total length is 10. I think we absolutely have to connect this vertex to the rest. The cheapest way to do it is by taking 5. Then we have to connect these two. And it feels like 2 and 3 are the shortest in this particular example. So finding, but I mean, it's an intuition so far. To prove that this is an MST, you need to either run an algorithm that is proven to be correct, right? Or loop over all possible spanning trees. So they loop through all possible connected subgraphs and calculate the sum and compare it to minimum. And obviously, looping through all possible subgraphs is an impossible task, right? Because you have, even if your graph is sparse, right, and you have around, let's say, 3 n edges, right? So you can take almost any subset of these sets and still remain connected, right? If you have around n squared edges, then you have like around 2 to the power of n squared subgraphs. And it is obviously impossible to loop through all these subgraphs, right? Because in practice, n can be up to 10 to the fifth, potentially around 3 times 10 to the fifth, I believe. In specific cases, up to 10 to the sixth, but these cases are very specific. We'll cover this later. So this clearly is not a viable option, and we need some algorithms to find MST. So originally, I believe the problem arises as follows. We have a couple of cities. We want to connect them by road network. We know the distance between each pair of cities, and we want to obviously to spend as little money on building roads as possible, because roads were pretty expensive in the past. They still are if you're going for high quality road. So that's it. Okay, so there are two main algorithms that you can use to find MST. They both have like specific use cases, but to understand why they work, there will be a couple of main lemmas. We will prove them as we prove algorithms. There are two algorithms. First is called Prim's algorithm. It's for dense graphs. There is a modification that works relatively fast for sparse graphs, but in practice, you will usually see Kruskal's algorithm applied to sparse graphs. So if you've seen the previous video, you may feel like it's the second time we talk about graphs, and it's the second time we have separate algorithms for dense and sparse graph. It's okay. It's a common pattern in graph theory. Like you will often see that optimal algorithms for dense and sparse graphs are different. It's just the nature of graph theory, I suppose. So let's first cover Kruskal's algorithm. In Kruskal, we will there are different implementations. The most efficient that I know uses a data structure called disjoint set union, so or alternatively union find. I'm personally attracted to the name DSU because it has the same number of letters as in a Russian name, which is, okay, it doesn't matter what is the Russian name for this data structure, but I personally use DSU. You may encounter union find. It's an operation that provides two operations, which are union of two sets and find the current set. So originally we have like n elements, each is contained in its own set. So originally this is first set, second, third, fourth, fifth, sixth. You can query this data structure like, please unite the sets 3 and 5. It will do something, it will unite the sets. And then you may query what is the current set of fifth element. And it will say like, oh, it's 3, because you just united them, right? And the interesting thing is that with optimal implementation, this joint set union works almost in linear time. So if you have like capital K operations, then you will have like very small constant times K. Constant is usually 4 for all practical applications. It is not, strictly speaking, it's not the constant, but it is in practice, okay? So if you are interested in this joint set union, I believe you can find some online, or maybe we'll talk about it later on in separate video. And it will explain like what exactly goes on with this constant, which is not really constant, okay? So it's a pretty efficient way to query for the current sets and union sets. And the reason why we want this data structure in the first place, because what we will do in Kruskal's algorithm, we initially create a separate set for each vertex. And then we say like, oh, we would like to unite some sets, right? What is the cheapest way to unite two sets? Well, it's by taking the minimum weight edge, right? So we take 2, so like, oh, it unites two sets. So then we take 2, right? And now we have two sets that look like these two sets are gone. Now we have like this set. And as you see, we will unite sets one by one. And it's a really convenient data structure. Like it provides exactly what we want. Because like it can unite sets and it can query for set. We will see why we need to query in a minute. So the next cheapest connection is 3, right? So we take 3 and we unite these two. So after we unite these two sets, we end up with something like that. We have one big set and one small set. And well, we drawn this edge and this edge. We also have this edge, right, with the weight of 4. And strictly speaking, like we understand that this is a current connected component. So these two vertices are already connected. But to check it, we can again use DSU. So we query what is the current set of this vertex and what is the current set of this vertex. When we encounter a new edge, we query whether or not its endpoints are already in the same set. If there are, they are, and we don't take the edge. Then we process the next smallest edge. Then we unite, and strictly speaking, we can just we need not stop it, right? Because then all the following edges will be discarded because these two endpoints will belong to the same set. So yeah, our initial MST was correct. It consists of 2, 3, and 5. So again, the algorithm is as follows. First step, you sort edges by weight increasing, okay? So by weight increasing, because you want to process the shortest. Alternatively, you can see the weights denoted as lengths, or sometimes cost, again from the analogies with road construction cost. So don't be confused when I use these terms alternatively. Okay, so we sorted edges and we process them one by one. Second step is a loop over edges. Check if find of first endpoint if it's not equal, if the current set of first vertex is not equal to the current connected component of the second vertex, or if they are not, then you want to unite them. And also you want to add this edge to MST. Okay, so these operations are supported by DSU. They are very fast, and the main difficulty is sorting edges. But sometimes you may be the luckiest guy alive, and you see like 10 to the 6 edges, and you think like, oh, I can't sort that many elements, or maybe it's very tight. But then you realize that, oh, a problem statement actually guarantees that edges are already sorted. And then you like almost 100% certain that you are asked about Crucial, because like, what else can it be? Problem statements don't sort edges just because they can, right? There must be some idea behind sorting. Okay, so now that we described the algorithm, it's the reasonable question arises, like, how do you know that it is correct? Why exactly this particular algorithm produces the MST? It may seem very like intuitive, right? You just take the smallest edge that is necessary to take, right? And we can indeed prove that it is by the similar reason. So let me clear some unnecessary steps. Because I will need this space for more drawings. In a second now. Okay. So suppose that MST of a graph contains some edge that we have not taken in the algorithm. So we ignore this edge. Well, how could we ignore this edge? Right? Well, we could ignore this edge. Yeah, let's take a look at what we actually produced, right? So we have some results in MST in which these two vertices are connected, right? So they are connected somehow, substantially like this. So they may be connected by like very long chain. And then we have like a strict edge between them that we did not take, like, or did not take. Why? Now, if these two edges were not connected, when we were processing this edge, then we would take it, right? Because we always take edge that connects new components that are currently not connected. So it means that by the time we came to that edge, all the red edges were already added. Red? But what are the implications? Like, what does it mean that all these edges were already added? Well, it means that we have some edge weights, V1, W2, W3, etc., W, I don't know, K, right? And we also have this H weight W. I accidentally written omega all the time. I apologize. Let me rewrite. We have W1, W2, W1 goes here, WK. Oh, and because this edge was processed after all of these edges, it means that all these edges are shorter, or alternatively have smaller weight than this edge, right? So what would be the point of adding this edge? Like, why would we want to add edge that has like higher weight than all the edges that connect this pair? We can't use this edge. It is impossible, okay, to drop any of the other edges and decrease the weight. So if we were to change the last edge to W, right, the graph would stay connected, but the total weight would increase because W is greater than WK. And the same goes for any other edge that we want to do it. Like if we want to delete W3, the graph stays connected, but it's impossible. I mean, it's not MST because W is greater than W3 because this edge is processed after this edge, right? So we can't change one edge to another and improve the total weights. But maybe you may ask, like, what happens if we like completely reconstruct the tree? So we change a lot of edges, right? And we will answer this question in a second. So mainly, this was intuition, and actual proof goes a little bit differently. So what we do instead in the proof is the following. We prove by induction the following claim. Like, suppose at some given moment in time, Kruskal's algorithm produces some subset of edges called capital F, right? We will prove that there is MST connecting all of these edges. How do you do it? Now, initially F is an empty set, and the proposal is obviously true. Like there is a minimum spanning tree containing an empty set of edges, right? Because empty set is a subset of any set, right? Suppose that we are in the middle of constructing MST. We have something like this. This is our current set F. And also, again, we can have like multiple components at any given stage. We also can have isolated vertices as well. So suppose we take, we consider the next edge. If it is inside of the current connected component, then we don't add it, right? Don't add it. And therefore, set of edges does not change, and proposal obviously holds. If this set of edges is a subset of some MST, then the same set is also a subset. Now, suppose that we do consider an edge that connects like different components. And suppose that like there was MST containing all of these edges, but there is no MST containing all of these edges plus this, right? Okay. Let's take a look. Let's take a look at actual MST. It will need to connect this somehow, right? Not necessarily like that, potentially in a somewhat more complicated manner. Potentially we'll have like that, and even like that. So now red and blue, suppose that red and blue forms MST, but there is no MST with green edge, right? How is it possible, you may ask? Like, these two vertices are connected in red plus blue graph, right? And when we add green edge to this graph, it results in a cycle, right? Minimum spanning tree is always a tree because it makes no sense to add like unnecessary cycles. You can always drop some edge of the cycle. And it's exactly the case. We have a cycle, and we can drop any of blue edges, right? There is a blue edge in this cycle because these endpoints of the green edge have to be connected, right? And they were not connected in red graph. So we can take any of the blue edges, remove it, and add green edge to MST. It will improve MST because green edge is processed before all blue edges and is therefore of smaller weight. So all blue edges are heavier than green one. So it obviously makes this graph is worse than this graph. We removed blue edge and we added green edge. Obviously, graph is still connected because like we created a cycle and then removed the cycle in different place. But it, yeah, if you like remove edges from the cycle, graph stays connected because all vertices of this cycle stay connected, while the path that remains. So yeah, it makes no sense not to take green edge because it's better than all edges that will follow, right? So that's why a cross-cause algorithm works. So at any stage, at any intermediate state of the algorithm, it contains some valid subset of edges. This subset can be extended to MST. Okay? Okay. I believe this explanation was relatively clear. So now you know how cross-cause algorithm works. Cross-cause algorithm runs in time. Yeah, let me remove unnecessary things. Cross-call runs in big O of n log n, where n is actually number of edges, right? Because you want to sort all the edges. And then you have relatively like cheap operations with disjoint set union that are dominated by this summand. Well, cross-call runs in this amount of time. If you have number of edges approximately equal to number of vertices, then it's a very fast algorithm, right? But if you have number of edges equal to approximately square of number of vertices, and this happens a lot in the problem, in the subproblem of MST called EMST, where E stands for Euclidean. So Euclidean MST is the same problem as before with some exception. Now we have like several points in a plane in three-dimensional space, whatever. The point is that we now have a fully connected graph. So all edges are present. We can connect any 2 points, any 2 points. It makes that graph is obviously dense, is a complete graph, has all the edges possible. And in this case, we get capital O of V squared log V, right? And because log V squared is simply 2 log V, and we can disregard 2 in big O notation. So this does not look very nice. What we can achieve instead for dense graphs is capital O, big O of V number of vertices squared, which is better by a factor of log. However, like in practice, if number of vertices is approximately 10 to the 4th, right? Log is what? Log is 14, I believe, and you also have this constant, so it of 2, then it makes log 28, and you get like 2.8 times 10 to the 9th operations if you use cross-call instead of 10 to the 8th, which Prim's algorithm gives. So the difference between these two, I believe, as you know, is this one is time limit extended and this one is accepted. So yeah, we clearly need a better algorithm for Euclidean Mst, which is commonly called EMST, right? So EMST. And EMST is a special case of dense subgraphs. For other dense subgraphs, it is also beneficial to use Prim algorithm. And Prim algorithm is a bit of a different idea. So let me draw some graph. Let me bring back the original graphs that we were looking at. I think it was like 2, 3, 4, and 5 and 6. Now, Prim's algorithm takes any vertex, absolutely any vertex. We can start with this vertex. Then it has like vertices of two kinds. Have processed vertices in green and the remaining vertices in like orange, some sort of orange, I believe. We do the following. We look closely and think, what is the shortest edge between green vertices and orange vertices? Like, what is the cheapest way to connect at least some orange to the processed part? It says like, oh, okay, it's 5, right? So we take 5, take this, we change unprocessed vertices to these two, and then we think like, what is the cheapest way to connect green with orange? Well, it's by taking 3, right? We take 3, say, okay, this vertex is processed, remain with only one unprocessed vertex, which is 2, this. And then we think like, what of the edges is cheapest way to connect? We think like, oh, well, it's obviously 2, right? So let's take 2, and we take the vertex, and we are done because we connected everything. So at every iteration, Prim's algorithm adds one vertex to processed part, and it adds in like via the cheapest edge possible. Okay. So. How to implement this thing? Let me go a couple of iterations back. Yeah, at this point. Now, the most efficient way to implement it, which works in quadratic time, is the following. You have obviously n or n minus 1 iterations. At each iteration, you add one vertex. Now, you want to add them via the shortest edge. Well, not a big deal. For every vertex, we will store the shortest incoming edge from green vertices to orange vertices. So initially, these edges are simple, right? You just, in every vertex, you store the shortest edge that goes into this vertex. In this vertex, for example, there is no such edge. So you may store like a value of plus infinity. There's no edge, right? And then you can do linear scan and choose the smallest of these numbers. So you chosen 5, right? what happens is that your vertex gets selected, this edge gets selected, the set of unprocessed vertices changes to this, and now you want to recompute for every vertex the new shortest edge incoming from green vertices. Well, obviously you changed only one vertex to green, so you only need to take a look at all of these edges. When you take a look, you may override some incoming edges. So this 4 is shorter than this 6. So actually we already know that this 6 will never get into any MST. Right? Then you again loop over all orange vertices. You select the shortest edge. It's 3. The corresponding vertex gets added to MST, right? There is only one unprocessed vertex remaining, and you want to take all outgoing edges from this 3 and check whether or not your edge is shorter. And in this case, your edge is 2, and there was an edge of 4, and 2 is shorter than 4. And you can already say that 4 is not a member of any MST whatsoever. Then you continue. So obviously you have a linear number of iterations. At each iteration you do 2 parts of linear work. First is to select minimum, and second is to recompute. Potentially there are n outgoing edges, and you want to select minimum of these guys. So overall complexity becomes n squared, where n is the number of vertices. Now again, a reasonable question arises, like why the algorithm is correct? Why exactly it produces MST and not some other spanning tree? Well, obviously it produces a spanning tree, right? It never creates cycles because it always goes to unvisited vertices, and it visits all the vertices. So it's a tree, and it's a spanning tree. It's connected to a graph. Well, the proof is like almost the same as before. We have some connected part. We have some other vertices. We again proceed by induction. We suppose now we would like to add this edge because it's the shortest connecting one of these vertices to the constructed part. We say like, okay, what if there is no graph with this edge, right? What if this vertex is connected to the rest in different ways? Suppose it goes like this, I don't know, probably like this, okay? And we again say well, blue and red graph won't be the best, right? Because there is an edge. Well, if we add green edge, then there is a cycle. And in this cycle, there must be a blue edge from the connected red part to one of these vertices, right? In this case, it's this edge. And this edge is longer than our green edge, because green edge is currently the shortest edge from the red connected part to other vertices. So this edge is longer than this. It means that this MST is worse than this because we removed longer edge and added a shorter one. We again came to a contradiction. So indeed, we need to add this green edge. That's why Prim's algorithm works. Now that you know how algorithm works and why they work, I find it important to understand why algorithms work because it's really easier to remember them and implement them if you know how, like not only how they work but also why they work. You have no doubts when writing code. You're 100% confident that what you write works. Okay, not because somebody proved it, but because you know yourself what the algorithm does, why it succeeds, and things like that. With that in mind, let's cover a couple of problems. We have 4 problems, I believe, today. Problems A and B are about cross-call. They have sparse graphs. Problems C and D are about Prim's algorithm. They have dense graphs. And you'll see the construction in a minute. So in the first problem, we have Honeyland. The Honeyland is some sort of kingdom or federation, I believe. It has like a grid structure, and you want to connect neighboring honeycombs, and you are given a formula that gives the length of the edge, right? So first of all, you notice that there are not all that many edges, right? There are like at most 6 edges from going out from every cell. It's a great sign. It means that the total number of edges is linear. Unfortunately, you have like a lot of vertices. You have at most 1 million vertices, and therefore around 6 million edges, which is not great. You may panic because you know that you can't sort like 6 million edges, and you obviously can't use Prim's algorithm because it would work in like 1 million squared, which is even worse than sorting 6 million edges. However, because of this formula, so then there you like compute some things, and you take modulo P2. Now, P2 is a prime number that is at most 1000. I'm not exactly sure why the number is prime, but the important thing is that it is at most 1000. So all edge lengths are at most 1000. So you want to sort a lot of edges according to their lengths, but lengths are at most 1000. And I believe that a lot of you will realize that it's a content sort, right? You can just create 1000 buckets according to lengths and then put every edge into the corresponding bucket, right? You do not care in which order edges are processed within the same bucket. So MST in this case may not be unique. They check only the length, the total length of MST. So yeah, that's it. I have my disjoint set unit data structure. It has some operations. As usual, nothing interesting here. Also, I have helper vertex ID, which basically converts like a row column to ID. I have like built graph function that effectively loops over all edges and adds edge into the correct bucket. So I have like vector of vectors of edges. First, they are indexed by length, and they whatever order they arrive in. And then I have cross-call algorithm, and you can see that cross-call is very short. So it takes like size of, it takes graph, it takes like vertex counts, and because I'm like very lazy, and I define graph using comment types, which you obviously can define your own data structure graph that will provide access to vertex counts. I did, so I have to pass it as well. Now I create this disjoint set unit. Then I loop over edges in increasing order of length, and I check whether or not this edge connects different components. If it does, then I take it into MST. In this case, I'm only concerned with the length, so I add the length, and I unite sets, and that's it. That's it for cross-call algorithms. It's really, really short. So main ideas here is that sometimes you have to use count and sort. We do. And any kind of grid structure results in a sparse graph, which is a very important observation. You may see like not necessarily hexagons, but rectangular grids. It also results in the same sparse graphs. Second problem, there's not much to cover. Like algorithms are very simple, both of them. So yeah, you just build graph, run cross-call, and that's it. Well, also you need disjoint set union, but I believe that you have something like that in your library, or you can always borrow my code. It's okay. If you find it like convenient, then you can use it. Again, all the code is on GitHub. In second problem, now legend is a little bit complicated, but the point is that we have some sparse graph with at most 100,000 edges and vertices. And we want to find all rods. Yeah, it's a road network, and we want to find all rods that are such that there is no cycle in which they are maximal, and it's another way to describe MST. So if H is not in MST, then and all edge lengths are distinct, then if H is not in MST, then there is some cycle in which this H is of maximum weight. And it's the proof of this lemma is like basically the same as we did in the proof of correctness of both algorithms. You can you take MST, you add this extra edge, and you find the cycle, right? So we are again tasked with finding MST. This time around, nothing interesting. We are given edges in increasing order already, but we could sort them anyways because there are not so many of them. But because we are given them in the correct way, we just again like manually loop over the edges, right? We check whether or not this edge connects to different components. If it does, then we this time around we are questioned with like outputting all edge IDs of edges in MST. So we add edge ID. I believe you can always use like this version, and then if you want length, you can write another function so that you don't have to rewrite this code. As you can see, like we have a pretty the good quality of this code is that like I just copy pasted the issue, right? So I did not retype it. It's exactly the same as in previous problem. And if your cross call is the same, and if you like, the great thing about these practice problem sets, like training problem sets, that if you write good code while solving them, then you can reuse this code later. So I definitely tried to write a reasonable code. I'm happy with changing one line, but I would not be happy like with changing the entire algorithm. So I try to create a separate function for that so that I can conveniently copy, and then in my main program, I just call these functions. And I also do some like simple input output, but you can get rid of this as well if you want. So yeah, use these trainings as a opportunity to write your own library, and then you just will reuse it, the same code on contests. It saves a lot of time, like really. Like implementing this disjoint set union again may not seem very long, but it takes like 3 minutes, 2 minutes, whatever speed you type at, it takes some time. And as you know, comparative programming cares about time. So yeah, nothing particularly interesting in this problem. Absolutely nothing. Except for this lemma. So if your edge is not in MST, then there is a cycle in which this edge is maximal. Okay. Remember this lemma, it helps find MST sometimes. Okay, let's head on to the next problem. We are given endpoints in Euclidean plane and only 200 points, whatever. Points have some coordinates. We want to join them. We obviously use Prim's algorithm for EMST. Prim algorithm keeps track of minimum edge going to every vertex, and because we want also like to not only to compute the length, but we also want to compute all the edges. So for that purpose, we will have like selected edge is points to vertex ID. So we have like length of the edge and ID of the vertex from which this edge comes. Just like that. So I believe if you like write your own data structure, yeah, then you can incorporate these two values into the same thing. I was lazy for some purpose and I didn't, so I have two vectors, but I changed them like at the same time. Two vectors and I change them at the same time. Yeah. You can go, you can start anywhere. For example, you can start at like vertex with index 0. You have other options like starting at random is probably better on average. Then you have a couple of iterations. You select a minimum edge, like looping through all edges. You process the selected vertex so that you add an edge to MST, and you loop over outgoing edges and update so minimum edges incoming into the not yet selected vertices. A bit more code, but still like it's very simple. You only operate with linear data structures. You have like a couple of for loops and a couple of if statements checking that this edge is shorter than this edge and such. Nothing particularly complicated here. Yeah, I mean, you can also create your own data structure for points. It's sometimes useful because you can have like distance defined on points so that you don't have to rewrite this thing all the time. Okay, I also use like somewhat interesting approach here. So I output MST as a vector of edges, and then I compute its length like in main program with std accumulate. Well, it's a viable option because I want both MST and total length. So I just have some accumulator variable which is set to 0, and I add all the distances of edges. Usage of lambda functions in standard library algorithms is pretty convenient. I believe we will soon have a training session about binary and ternary search and also binary search over the answer. I've heard such requests, and we have corresponding training session. It's from 2012-2013 season, as opposed to 2013-2014 we are currently solid. It's not a big deal. It's of approximately the same level of difficulty. Yeah, and it's about binary search. We will see a lot of applications of this approach. So passing lambda functions to algorithms is very convenient, especially in binary ternary search. We will see examples in the next training. So here is like foreshadowing of what is about to come. The last problem is like bigger version of the same problem. We have like at most 5,000 cities, and also the coordinates are a bit bigger, but we don't care. Yeah, we do the same thing. Like this has not changed at all. It's the same. It's almost the same. Like, only in this case, we don't even have to output the MST itself. But yeah, like it is literally the same. You can look at it this way. It's the same. You take this, it's the same. Here we also output MST itself, here we don't. But then it's again the same. Distance, 3 points, premium EMST, it's the same thing. That's really useful to write reasonable code so that you can reuse it again. Because it obviously saved me a lot of time separating it into like separate function. Yeah. I would spend so much more time if I were to write it from scratch every time I need it. That's really helpful to have something like this. Also, I would say like converting point to template would be helpful. The same goes for edge. So that you can like have not necessarily integer coordinates, but like floating point coordinates. In case you come across a different problem in which coordinates are not necessarily integers, then it would help. So yeah, write reasonable code. You will appreciate doing it on the very next contest where you can reuse it. I feel like that's it for today's training session, and we'll be back with binary search, ternary search, and binary search over the answer training very soon. I'm not sure about today. It's evening already, but maybe I'll record it today and like release tomorrow. So stay tuned for more content. I hope you enjoyed. I hope it was helpful, and it certainly was helpful for me because I did not have like this template algorithms before. I really think that I will appreciate. I will be happy with myself that I did it, because like for example, 3 days ago, I believe I was writing like code chef contest by trace, and then next day I was solving some lead code questions, and I just reused data structures that I implemented for code chef contest. It was very easy to reuse because I wrote reasonable code that it's adaptable and yeah, easy to adapt basically. I didn't have to change like any code of data structure. I just needed to process queries to this data structure, so it was really useful. And the same goes for graph algorithms, of course. Beyond any doubt, you will benefit from implementing a lot of template algorithms. What can I say? So yeah, I think it was it for today's video. Write reasonable code. Have happy holidays, because like today is January 1st. I'm certainly having happy holidays. I was outside. It's marvelous. Yeah, very good weather we're having nowadays. I hope I have high hopes for 2021. Um, Both like in general and regarding this YouTube channel in particular, I see a lot of support for the series, both on Codeforces and CodeChef and LeetCode even, despite having some controversial with LeetCode stuff. But nothing particular bad, it's all manageable. I hope this year will be better for all of you guys. Hope you enjoyed, and see you